the side here. Let's say you did your row reduction stuff and you got something that looked like that. Okay. All right. So it's a very good question. It's stuff we're going to talk about today anyway. So let's say we're going to have something along those lines. All right. So if we think about it with 4 variables, this would be, say, your x1, your x2, your x3, your x4 columns, right? Okay. When we have these, we don't have any information from the table, from the matrix for the x3. We don't have any information for the x4. But if we did have information for x3 and x4, I could get what the x2 is and I could get what the x1 is, right? Okay. So in this case, you're exactly right. We would want to write those as parameters. So in general, we refer to these as what we call free variables. So the free variables correspond to these columns that don't have any pivots in them at all. Right? So anytime you have a free variable, that's going to be represented with a parameter. Because those we can choose whatever we want for the x3. We can choose whatever we want for the x4. Usually we start with our parameters being t, and then we work backward through the alphabet from that point. So if I have a t for my x4, I'll use an s for my x3. But again, once I have those, we should be able to figure out what the x2 is and what the x1 is from that. Okay. So looking at the second row, I'm going to write this off to the side, and then I'll write the solution back over here. What equation would come out of the second row?
x2 plus x3 plus 2x4 equals -1.
Good. That would be that would be what would come out of the second row, right? Well, if I put in S for the x3, representing that I can put in whatever I want for x3, and the t for the x4, we can now solve for the x2, right? We just subtract over. So we would have, I'll write it as -1 minus s minus 2t in that case. All right, so what would you get for the, yeah, Matt?
I totally missed it. 2x1. Oh, that says okay.
Yeah, that's 2x4. Yeah. That's an x4. Yeah, that's just a bad handwriting. That's a 4. There we go. That looks a little better. Yes.
Why didn't we just use the normal Gaussian?
I already did. I'm saying that we already did the Gaussian elimination and got to this point. That's my final reduced row echelon form. Okay. And so now I'm just interpreting the solutions. What would the x1 be equal to?
5 plus 2x minus 2.
Good. I got my constant 5. You need to move the 2s over, right? Should be able to do it without having to write the equation down. It's just a matter of flipping it to the other side, right? Plus 2s and then minus t. And then, so this would be a perfectly fine answer. Sometimes you'll see it written as ordered tuples. Perhaps even a little bit better. And this is what we'll be concentrating on later as well. So we'll just go ahead and write it this way. Maybe you'll write your answer as we will refer to as a column vector and separate it into 3 pieces. There should be a piece that just has the constants. There should be a piece that just has the coefficients for the s. And there should be a piece that just has the coefficients for the t's. So let's go through how I did that. Looking at your answers here, your x1 has a 5 in it without any parameter. The x2 has a -1 in it without any parameter. The x3 and the x4, there aren't any constant pieces, right? Because they are the parameter. Okay. So this is just picking off the constant pieces. So x1 had a 5, x2 had a -1, 0, 0 for the x3 and the x4. If you think about it as tuples, I'm just writing it vertically. Okay. So if the values for s and t, for example, are 0, that would be your solution, right? 5, -1, 0, 0. That's an example of a single solution, right? If I put in 0 for S and I put in 0 for T, or likewise, if I put in 0 for X3, but if I put in 0 for X4, my answer would be 5, negative 1, 0, 0. That's what we have here, right? We refer to that as a particular solution. Particular solution because it's for a particular value of the parameters, namely what you get when you put in 0. Okay. Looking at the other pieces here, notice that if I ignore the part with the t and the part with the constants, I have coefficients here. Everything has an s in it, except I have a 0 here, right? So my coefficients for my s's, there's a positive 2 for the x1, a negative 1 for the x2, a positive 1 for the x3, and a 0 for the x4. I'm just collecting those there. Notice that if you're familiar with vectors from Calc 3, for example, I could just take that constant and multiply it by each coefficient or coordinate, right? Each component. Likewise, the same thing for the t's here. If you've added vectors before, physics class, calc class, whatever, you would just add your coordinates across. I'd have a 5 plus a 2s minus a t. I've got a negative 1 minus an s minus a 2t, and all the way down, which is exactly what we have here for those different answers for the variables, right? Notice that, and this is going to be stuff that we're going to talk about later as well. Again, I referred to this as a particular solution. Maybe I call it XP. Over here, notice that anything I plug in for S and anything I plug in for T, if I ignore the constants, will give me 0 for all your variables. By the way, things are set up. If I plug in, pardon me, the way we have it set up for the equations here, if I put in 0 here, I know that my S plus my 2t is 0, correct? What it says we have to have, and likewise for the other ones. So if I ignore the constants, any value for S and any value for T is going to go back up and solve your system to give you 0 rather than the constants, by the way the system is set up. So this turns out to be a solution to a general solution to your homogeneous system. If you just replace the constants with zeros, these would be all your solutions to the associated homogeneous system. So again, we're going to talk about this stuff later, so if it's not making sense right now, we're going to come back to it and make it more formal. But any solution that you have to a system of linear equations, I can write it this way. I can write it as a particular solution to the non-homogeneous system plus the general solution to the homogeneous system. And if you've seen differential equations, may or may not have seen differential equations, but if you've seen differential equations, it's exactly how you solve a non-homogeneous equation. You find one solution, you find a solution to the homogeneous, and then you work to find a particular one, and you can write all your solutions this way. If you're in differential equations now, same idea. Right. We'll formalize this more later, but right now, are we okay with just taking your answer and writing it in this form and not worrying about the details? Are we okay with writing the answer that way? Okay. Other questions?
What's that form called?
This form, it doesn't have a particular name. We call this the particular solution, and then the homogeneous, the solution to the homogeneous. It doesn't really have a name, but not that I know of, at least. Yes.
So we can always write the solution that way with this.
We can always write the solution in this fashion. Yes. We can always convert what we have this to this one. Yeah, every single time. Are we okay with the row reduction process? Get 1, get zeros, get 1, get zeros. Okay, so let's talk a little bit then about how we can use some technology to help us. We've got a couple of examples of a couple of different things here. Let me show you the computer first, a couple of options on the computer, and then we'll do calculator, because many of you may probably want to know how to do it on the calculator, especially if you're using it for a quiz or an exam, or not a quiz, an exam. So, but I wanted to show you a couple of things on the calculators that are online that also can help you. So we talked about GeoGebra a little bit, right? What I would do when you're dealing with things with GeoGebra, especially if you want to do things with variables in them, I would change your view over to take off the algebra view and put in the computer algebra system view. If you've got anything with variables in it, it's nice to be able to do it that way because it'll handle the variables. If you leave it in the algebra view on the left-hand side, it'll only deal with things that you type in with numbers. Okay. All right. Another thing that was weird. I don't care. Go away. Another thing that might be helpful, typically we're not going to worry about graphics. However, with entering matrices, it might be a little bit easier to have your spreadsheet up on here, and here's why. So, flipping back over to one of these problems, let's say you wanted to solve I know this one's telling us to solve with Gauss-Jordan, but let's say we wanted to use our calculator to solve this instead. Okay? What would your augmented matrix look like in this case? What would your first row be? Okay. And then, good. Good. We okay with getting that part set up? All right. I'm going to use 3 different technology resources to solve this. Okay. And then we'll probably focus more on the calculator. It's just harder for me to type things in on the calculator on the computer because I don't have an emulator on the main computer. The document camera isn't working on the main computer, so I had to use the emulator that I have on my Surface here, which is a little bit clunkier to use. So that's why I was going to use the other technology. All right, so let me flip back over the screen here real quick. Going back over to GeoGebra here. I can type in this matrix. I don't have it up on the screen right now, but you should have it on your paper. I can type these into the cell in GeoGebra's spreadsheet. I can do 1, -3, 2, 1. Oh, hey, where's the 3? Oh, the number lock was off, I think. The number lock's not working. That was weird. 3, 2, 1. All right, and then 2, -1. 2, -1, 2, 0. Thought it'd be easier to type on here. Apparently it's not for me. 1, 1, 1, 6. All right. I think I've got everything typed in there correctly now. Okay. I don't have the vertical bar here. That's okay. We can understand the vertical bar is there, right? We should know that that's where the equal sign would be. What's nice about this for typing purposes is that if I highlight it like you would in Excel and right click, and then apparently, for some reason, got off that last one, I can create lots of different things, but in particular, I want to create a matrix. Okay. Once I do that, well, it didn't show me. It's probably over in the algebra window. There it is. It's over in the algebra window. I can see it, so I'll leave it up there. It created the matrix from those cells. It also gave it a name, so I can go back and refer to that name each time. You can do the same, like I said, a lot of times you'll do the computer algebra system. Sometimes you can just get away with the algebra if you're just doing things with numbers. So I'll just do it over here in this window. It doesn't really matter which window you have it in. It'll just show you what you've got for your variable names over here in the algebra window and not in the computer algebra system window. All right, so now if I want to put this in reduced row echelon form, I go back over here. I'll use the algebra window, even though I said do the computer algebra system. It doesn't really matter for our purposes. Notice I just started typing reduced row echelon form. Pops up as the command. So I'll do reduced row echelon form. The matrix name is M1. I can type M1 in there, hit enter, and it puts it in there for us. And it does it pretty quickly. So this is our reduced row echelon form. How many solutions does the system have now? 3. Well, when we're a solution is the values for all the variables that we have. So we just have how many? Just one, right? Just one solution here. The x1 is, the x2 is, and the x3 is 11. That was pretty quick, right? I like GeoGebra for doing these matrix operations mainly because it's a lot easier to type them in. All right, I can type it in a spreadsheet and tell it to make a matrix, and then I have my matrix. Because I can use the tab button and I can type it in pretty quickly like you would in Excel. So I think it's a little bit faster than the calculator. Though again, on an exam, you'll have your calculator. So we'll do that here in a second. But are we okay with this and the interpretation of the answer? Desmos, many of you may have already used Desmos in other classes for a graphing calculator. Desmos is wonderful for graphing calculator, but it also has some matrix commands too. Now notice down here you've got many other math tools that it says, so I can click on the matrix calculator that it has. Desmos also has an app. The problem is that the app doesn't include the matrix calculator. Otherwise, I would tell you about it. But if you want a portable graphing calculator that's really easy to use, I would get the Desmos app. It's free. All right. Ooh, hey, that was much bigger than I wanted. All right, so notice here, I can say make a new matrix. I've got letters here that you can store your matrices in. Notice that if I hit new matrix, the first thing it does is to call it A, so then I can refer back to the A again. This matrix had 3 rows and 4 columns, right? So again, I can type in, notice that I hit enter and it just entered it in without typing the other things in there. So I want to use tab most likely. I can type in my entries, much like we did with the spreadsheet over in GeoGebra. And hit enter. And now you've got some matrix operations. We haven't talked about these other two down here, but notice it says RREF. Click that. Put in the matrix A, hit enter, and you've got the same exact answer we had in GeoGebra. I wish I had this in the app because that's pretty nice. You'll be able to do that on your phone too. Okay. All right. So again, like I said, I just want to introduce you a couple of the different technology tools. We have the technology tools. We might as well use them, right? Excel isn't particularly nicely set up for linear algebra types of things. You can do it. I think you can download a package and have it do your row reduction, but generally speaking, Excel's not great. Excel's a great computational tool, it's just not necessarily great with linear algebra technology. Thanks. All right. So let's go and look at the calculator, because that might be what you're most interested in anyway, or tired of listening to me talk about these things. All right, so let me flip back over to my laptop. I got to grab my calculator. There's my calculator. This is a very old emulator for a TI-83. However, it has the same... where'd it go? There it is. It has the same functionality as your 84s do for what we're going to be doing for matrix operations, and they're all in the same place. So not too big of a deal. All right. So the best part about this particular emulator, at least from an amusement standpoint for me, is it literally emulates the calculator. It will turn itself off if I don't use it. So if I hit click it back on, even though it's on the computer, it will time out and turn itself off just like a calculator does. Just kind of amusing. All right, so I have to turn my calculator on. Matrix menu is the one you're going to be most interested in this class, which should be right next to your math button. Okay. When you click on that, you should see those options. You should see names, you should see math, and you should see edit. Names is where you're going to go to grab it to do any operations with it. Okay. The first thing, though, anything you're ever going to do is type in a matrix. So you're going to want to go over to the edit. You can pick whichever one you want. I'm going to pick A just because that was the first one. First thing it's going to want you to do is put in the dimensions. So in this case, we had a 3 by 4, right? And then it will go through, each time you hit the enter key, it will tab across the rows. So as you type it in, it will go across the rows. So we'll do 1, -3. Make sure you use the negative sign and not the minus sign. It will give you an error if you put -3 rather than -3. Okay, so you'll only use your negative at the bottom and not here. 2, 1, 2, -1, 2, 0, 1, 1, 1, 6. Once I hit the last enter, it shouldn't go anywhere. It should stay there at the lower right-hand corner. Now we'll exit. Once you get that typed in, we'll exit out so that we can start using this to do operations with. So I'll do second quit to get out of there. I'll go back in again to my matrix menu so I can go grab the command. Again, if we want to put this in reduced row echelon form, I need to go get that command, scroll over to the math menu. There's lots and lots of different things, right? There's the determinant, there's the transpose, there's the dimension of the matrix. I honestly don't know what fill does because I've never used it. This one gets to the identity matrix. This creates a random matrix. There's lots of different things in here, okay? If you've got 2 matrices typed in there, you can augment them. All right, so there's lots of different things. Notice here at the bottom even, you've got row operations that you could do. So if you're doing this by hand, and again, I want you to be able to do row reduction by hand. This, you can check your answers if you use those row operation commands in there too. And it saves you some arithmetic. Okay. All right. What we're interested, of course, is the interpretation of the answer, right? So notice there's a row echelon form and a reduced row echelon form. We're not ever going to use the row echelon form command because reduced row echelon form, I can just read the answers off, right? The row echelon form saves you some computations, but generally speaking, it's not very helpful for us to read the solutions off because then we have to go back and do the back substitution. Okay. So we'll do reduced row echelon form, and then I'll go back in my matrix and grab A from the names menu, and then I can or don't have to close off the parentheses as long as it's the last thing I want there. And notice I got the same row reduction that we had for the other two. Good news is all the technology agrees with each other. Okay. We will use some of those other commands in the matrix menu, but in particular, the reduced row echelon form will be the ones that we can get to the final answer. Is that okay? So let's see if we can set a couple of these other ones up, use the calculator to help us solve them, and then we'll do a couple of application problems today as well. So let's look at this next one. First thing we would want to do is write down what the augmented matrix is. So in this one, what is our augmented matrix going to be? Okay. Good. Everybody okay with getting that set up? Okay. And again, are we comfortable with doing the row reduction? We do more another example if we want, but I just want to make sure we're okay, right? Get a 1, get zeros, get a 1, get zeros, stair step down. Okay. All right, so go over, type in our matrix. I can either overwrite A, it has the same dimensions, or put in a new one. I'm just going to overwrite it because I don't need the old matrix that was in there. It's still a 3 by 4. 1, 1, 1, -1, 3, -2, -4, 16, 5, 0, off, -2, and 3. good news is here that since I wrote it over A and I want to do the exact same thing again, I could go back into the matrix menu, go grab RREF, and then go back in and grab A. But your calculator will bring up the previous entries. Actually, if you've got the 84s, you can just go up and grab the thing, right? But on this particular calculator, I can do second and hit enter, and it brings up the previous entry. It actually stores the previous 8 ones in it. I believe it's 8. So if you just keep hitting second entry, it'll just cycle through the last 8 things that you typed in your calculator and then go back over again. So I know that on the 84s now you can scroll up with your arrow key and go grab it that way. But if you're just doing the previous one, it might be just a little bit faster to do second entry and just have it pop down. Or especially if you want to go back up 2, you hit it twice and just pop it down so you don't have to scroll and hit enter. That's just my personal preference. You can do whatever you want. It's your calculator. Okay. All right. Here's our reduced row echelon form. And this is what I mean by I want you to know how to do row reduction for this first exam. You'll need to be able to do those things by hand. But going forward, we're going to use the technology, do the row reduction on the technology, and then do the interpretation. So the previous example, the interpretation was I saw a single solution, I got an answer, I wrote it down. Or I should have written it down, but I didn't. Okay. This one, I want to interpret what's going on. What can you say about this particular system?
No solution.
No solution, right? Again, this is the augmented bar is here, even though we don't have to see it on the calculator. But notice what does the last row tell you? 0 equals 1, right? So this last row, when we put it in reduced row echelon form, when we put it in reduced row, oh wait, negative 4 and 1.4. I think I can remember that. Negative 0.4. 0, 0. Okay. That's what we got for our reduced row echelon form. So this last row here is telling you you've got 0 equals 1, so you've got no solution. So notice what happened in this case. And this is another interpretation that we're going to come up with later on in the semester, but I'm going to go ahead and notice it now. Remember, what did we call these leading ones? What name did we give for these leading ones? Pivots, right? Notice that in the third row, where did the pivot end up? It ended up in the constant column. That's bad for solutions, right? We ended up with an extra pivot when we augmented the matrix. Okay? Notice that if I would have row reduced this matrix without the augmented, I only get 2 pivots. When I augmented, I got a third, right? So the number of pivots went up, which causes an inconsistency in your solution. You get an inconsistent system. You don't get any solution in that case. So if you augment and the number of pivots goes up, you get no solution. Okay, that's true for anything. There's a name given to number of pivots in a matrix. It's called the rank of the matrix, and we'll talk about rank later in the semester. Okay. All right. Let's do the next one, because these are so much fun. Did you have any questions about the previous one? Notice these are much faster when you use the technology, aren't they? Negative 4, negative 1, 2, 3, 3, 3, negative 1, negative 1, negative 1, 2, 1, 2. Are we okay? And again, I'm assuming everybody's okay at this point for setting up your augmented matrices. Not too bad, I hope. All right, so again, let's go ahead and type this in and see what we get. I've got everything having the same size here, so I might as well just keep using A. I've got negative 4, negative 1, 2, 3, 3, 3, negative 1, negative 1, negative 1, 2, 1, and 2. just going to put that in there so I can make sure I've typed it in correctly since I did it fast. Okay. So now when we row reduce, notice in this case when we row reduce, it's giving us some decimals. Perhaps you don't want to see the decimals and you'd rather see fractions. You're probably familiar with this already, but remember your calculator will convert decimals to fractions if it knows what it is, right? If it's not too big of a denominator or not an irrational number. If you go to math and then hit option number 1, it converts decimals to fractions. I can use that for my matrix as well, and it'll convert the individual ones to fractions. If you've got the 84s, you've probably got a little bit prettier print, right? And you write your fractions vertically rather than horizontally, like I've got down here. I don't have the nice fancy emulator on here. All right. Looking at our matrix, is this what everybody got when they did it? If you're following along doing it. Okay. All right. Notice that in this case, when we look at that last row, what does the last row say? 0 equals 0. So that is it inconsistent, or are we still okay? It's still okay, right? It's going to be consistent, right? Notice, however, we've got that column that doesn't have a pivot in it, right? The X3 column here doesn't have a pivot. We refer to that as a free variable again. That's what we call those as free variables. Free variables mean that I can pick whatever I want for that value, right? So this has got one free variable in it. So don't have these on the screen at the same time, so I can shrink that a little bit so I can actually see what I'm writing. 1, 0, negative 5 ninths, negative 8 ninths, 0, 1, 2 ninths, positive 5 ninths, and 0, 0, 0, 0. All right. Pardon me. So column 3 is your free variable. So if I write x3 is equal to t, what does x2 equal? Good, 5 ninths minus 2 ninths t. Because again, remember, we would plug in the t for this x3 and then move it over to the right-hand side by the sign flips. This sign doesn't flip because it's already on the other side of the equal sign, right? But we're subtracting over, so the sign changes. So what do you get for x1 then? Are we okay with that for the solution? Does it make sense where we're getting those? Okay. Again, if we write it in that vector form, or what some books will call parametric form, I would write it as a column vector. What's your particular solution, or what's just the constants? What would you have for that first vector? I have negative 8 ninths, 5 ninths, and 0 because those are the constants that I see. And then your second part, everything has a t in it. Then what goes here? Yeah, you're right. Okay. Be a 1 because the coefficient on that t would be a 1, right? So it'd be a 1. Yeah. Is that okay? Is this okay so far? All right. Are we okay with interpreting the solutions, or do you want to do one more? Do one more? All right, let's do the next one then. Might as well. Doesn't hurt. That's what we're here for, right? All right. So again, first thing, we're going to make our augmented matrix. What size is your augmented matrix going to be? 4 by 5, right? Oops. So the first row, everything's lined up nicely. So I've got my -3, 9, 1, 7, -7. So as I go across, I've got X, Y, Z, W. Again, order of the variables doesn't matter as long as you're consistent as you move from row to row, right? I don't want to use my X for my first column in the first row and then use my Y in the first column in the second row. The order doesn't matter as long as you're consistent as you move down and you know what order you've used. Okay. So the next one would be 2, -6, 1, -3, -2. Now, notice here in the third one, the Z is missing. So I need to make sure I put a 0 in that third column to represent that the Z is not there. And then -1, 3, 2, 4, -9. Notice my calculator shut off because I haven't used it for a while. I find it amusing. I'm easily amused, though. Be more amused if I could get it to turn back on again. Why are you not turning on? Where's my mouse? There it is. There it goes. All right. Again, doesn't matter where we type it in. I'll just overwrite A again. But I do need to change the dimensions this time, right? It's a 4x5. -3, 9, 1, 7, -7, 2, -6, 1, -3, -2, -2, 6, 0, 4, -2, -1, 3, 2, 4, -9. Again, just real quick, I will bring that matrix back up and make sure that I've typed in everything correctly. -3, 9, 1, 7, -7, 2, -6, 1, -3. Because honestly, once you start using the technology, the biggest issue students typically have is typing all the numbers in right. Okay. All right, same idea now. Let's row reduce. Oops, that's what I wanted to do. That's what I wanted to do. This is why I wanted calculator otherwise here. So when we put this in reduced row echelon form, we've got 1, -3, 0, -2, 1, 0, 1, oops, sorry, 0, 0, 1, 1, -4, and then a bunch of zeros. So is this consistent or inconsistent? Start there. It's consistent, right? No issues there. Everybody else got when they put it in? Is that what you got? Okay. My guess is you maybe got one entry that's off. Check your entries again. As usually happens, if you got an entry that's off, it'll do that. Which ones are your free variables? Which columns don't have a pivot?
2.
Yeah, the second column, that corresponds to which variable? Y, and then W as well, right? So those are where your parameters are going to go. So again, we've got 4 variables, X, Y, Z, and W, right? Okay, your Y is one of your parameters and your W is the other. Now, the other examples we've done, if we had more than one parameter, it seemed like they were on the rightmost columns, right? Doesn't have to be. It's where the columns don't have a pivot. In this case, column 2 did not have a pivot and column 4 did not have a pivot when we put it in reduced row echelon form. All right? So that's where your parameters are. So now working on your variables, Using the second equation, we can figure out what z is. What does z have to equal? Yeah, -4 minus t, right? Because I would put the t in here for the w and then move it over. What's your x going to be? Yeah. Yep, that'll be a 2t and 3s. We'll write it that way since it's in alphabetical order. All right, again, you're going to put in s for y and move it over. So that's where the plus 3s comes from. You're going to put in t for w and move it over. That's where the plus 2t comes in. So now again, if we write this in parametric form or that vector form, if I write it in those column vectors, how would I write that? What's your first column going to be? Yeah, so be careful. I got to make sure I got them lined up, right? I got a 1 for my constant here. There is no constant here, right? So that's 0, -4, 0. We okay with that? What's going to get multiplied by your s? 3100. Good, 3100. And then what gets multiplied by your t? Good. Questions on that? Yes.
Could you not figure out the y and w and then y is to basically.
Which column is this pivot in? X, Y, Z, or W? Which column is that one in? X. Which column is that one in? Z. Okay. Those are the only columns that have pivots. The other ones do not have pivots in them. So those are the ones that we have to use for the free variables. There's no pivot in the Y column. So that's why the Y is one of the parameters. There's no pivot in the W column. So that's what we use for the other parameter. That's not a pivot, though. Remember, the pivot is the first non-zero entry in the row. Yeah. Even though the coefficient's a 1, that's not a pivot. It's the when you go in your row, it's the first one you hit is the pivot. The other numbers don't matter. Okay. That okay? All right. So that's pretty much Gaussian elimination. The last problem is just a application problem. I'll leave that one for you for practice. I do want to start. Oops, that's not the right folder. I do want to do a different type of application, though that was just setting up a system of equations. The other applications I want to talk about apply to kind of sciencey types of things. So we're going to talk about networks. We're going to talk about electrical circuits. We're going to talk about chemical equations. This is the 3 applications that we're going to talk about here. These are problems that I stole from another textbook. Or what academics like to call, usually for academic purposes. None of the green, that even as well, that's for sure. All right, so the idea behind these is to set up a system of equations and solve. So let's look at the network flow ones, and then we will talk about the circuits and the chemical equations on Friday. So let's look at this first example. Number 1.4, 1.1, part A. So it's a little past the reading. It should say page 29 at the top. All right, so we're just looking at this first application. The idea here is to make up a system of equations to help you figure out what the flows are in those different pieces. So maybe you've got pipes, maybe you've got electrical networks, what have you. But there's a flow going from this point to that point. There's a flow going from this point to that point, and so on down the line. And the arrows are telling you which way the flows go. Okay. We've got 5 variables here. We want a solution that makes sense for the 5 variables. So what we're going to do is we'll look at each of these nodes as we go along and make up equations. And the idea here is that if you've got this system, ins and outs have to be the same at each of those nodes. Whatever's going in, what has to come out, right? So if we look at that first node, if we look at the first node here, let's look at the top one. What's going into that node? F1 and F2. What's coming out? 50. So can you come up with an equation that represents what goes in, what comes out? F1 plus F2 equals 50, right? Does that make sense? Okay. Let's look at the middle left one. Let's look at this node right here. This one right here. What's going into that node? What goes into that node? This one here. What goes into that node? 40. And what? And F3, right? What comes out? F1 and F4. So what equation would you have? Good. I like how you already put it into the form that you would need to put all your variables on one side, right? I can think of it as F1 plus F4 equals 40 plus F3, and then subtract the F3 over. Okay. What about this node right here over on the right? 60. Okay, 60 is going in. Yep, F2, F3, F5 are leaving, so what equation would you have? So I wouldn't use the minuses. So the F1 or F2 plus F3 plus F5. So that's the out has to equal the in. Yep. We did the minus F3 because we would have subtracted it to the other side. Yep. And then finally, using the last one down here, what equation do you get? Good. So notice in this case, we actually have only 4 equations. We have 5 unknowns. My equal sign's missing. So we actually would get infinitely many solutions. So what we'll do next time is we'll get the solutions and then talk about interpreting what the answers would be. And then we will also talk about the other applications with circuits and chemical equations. So we'll do that next time. I also have a homework assignment that I want to give you. It'll be due on Monday. But we'll finish this up on Friday, as well as get into switching gears a little bit and talking about matrices. We've already talked about matrices a little bit. What we're going to talk about is operations on matrices. So we'll define what they are and do some operations stuff with those. So talk about that on Friday. So have a good one, everybody. We will see you then.